Today, we're tackling a problem that asks us to find the largest possible difference between two numbers in an array. The catch? The second number has to come after the first one, and it also has to be larger. Given an array of integers, our goal is to return the maximum difference between array j and array I such that j is greater than I, and array j is greater than array I. If no such pair exists, meaning no element has a larger element after it, we should return -1. The input is a simple array of numbers, and the output is a single integer representing that maximum difference. A straightforward, albeit inefficient, approach is brute force. We can iterate through every possible pair of elements. We use a nested loop. The outer loop picks the first element, nums I, and the inner loop checks all subsequent elements, nums j. If nums j is greater than nums I, we calculate their difference and update our maximum difference found so far. This works, but checking every pair leads to a quadratic time complexity, O(n squared), which becomes very slow for large arrays. Space complexity is constant, big O of 1, constant time, as we only use a few variables. The key insight to optimize this is realizing we don't need to reevaluate the minimum element for every potential j. As we iterate through the array, for any given nums j, the best nums I, where I less than j and nums j, will always be the smallest element encountered so far up to index j1. So, we can maintain a variable, let's call it min so far, which stores the minimum value seen from the beginning of the array up to the current position. We initialize min so far with the first element. Then, we iterate from the second element onwards. For each nums I, if it's greater than our min so far, we calculate the difference and update our overall maximum difference. If nums I is not greater than min so far, it means nums I is a new smaller value, so we update min so far to nums I. This single pass ensures we always have the best possible left element to pair with our current right element. Let's trace this with the example 7, 1, 5, 4. We initialize min so far to 7 and maxdiff to -1. Moving to the second element, 1. 1 is not greater than min so far, which is 7, so we update min so far to 1. Next, 5. 5 is greater than min so far, which is 1. The difference is 5 minus 1 is equal to 4. This is greater than maxdiff, -1, so maxdiff becomes 4. Finally, 4. 4 is greater than min so far, still 1. The difference is 4 minus 1 is equal to 3. This is not greater than the current maxdiff, which is 4, so maxdiff remains 4. We've processed all elements. After iterating through the entire array, our maxdiff variable holds 4. This is the correct answer, as the pair 1, 5 yields the largest valid difference. 5 minus 1 is equal to 4. You'll often spot this min so far or max so far pattern when a problem asks for a maximum or minimum value derived from a pair of elements, where one element must appear before the other. It's a strong signal for a single-pass solution, often involving dynamic programming principles. This optimized approach achieves a linear time complexity of big O of n because we only iterate through the array once. The space complexity remains constant at big O of 1, constant time. This min so far technique is extremely versatile. Try applying it to other array problems. Hit that subscribe button for more efficient algorithm solutions.